QuantumATK is a versatile application for materials research with tools for the entire materials modeling procedure, from structure building to performing calculations to visualizing and analyzing the results thereof. In a field where most computational tools are script-based, QuantumATK offers a fully fledged graphical user interface known as NanoLab, which can help guide you through even the most complex research topics. As I mentioned at the top, we'll be going through how to set up a simple research project in QuantumATK to calculate the band structure of bulk silicon carbide. We begin by creating a new project called SIC Tutorial in a dedicated folder. If we now launch into the main window, you'll see this folder down in the data sources as the project folder. So this is the main storage location for all files related to this project, but you can also add additional sources. This view we see now is called the data view and is the main place to organize, analyze, and otherwise use any data produced in the project. On the left side is a toolbar containing all of the major tools we have available to us, which is also conveniently ordered top-down based on how a typical modeling procedure is performed. Briefly, this begins by selecting an existing atomic model from the data view or creating a new one using the builder, setting up the desired type of calculation and workflows, running the calculation or job in jobs, and then returning to the data view to analyze the results. Since this is a new project, we have nothing to start with yet, so we need to go into the builder. In the center, we have a 3D viewport. To the left is a stash of all builder-created structures in this project. To the right is a list of various tools to help with the structure building, and at the top we have a toolbar of builder-specific functions. We'll start easy by adding a pre-made silicon carbide structure from the built-in structures database of QuantumATK. Clicking on the Add Structure button, we select From Database. As we can see, there are different databases for different types of structures, but we want a crystal, so we search the crystal database for SIC. And now we have a bulk silicon carbide model in our stash. At this point, we could manipulate the model further, for instance, by repeating it or tweaking the unit cell. But we're actually happy with the basic model, so we'll just go ahead and send it to Workflows. That will automatically open the Workflows window, which has a similar structure to the builder. In the center, we have the current workflow. On the left is a stash of all workflows created in this project, and to the right are blocks we can use to expand our workflow. Our silicon carbide structure is already there, so next we need to add a suitable calculator for a band structure calculation, for instance, the LCAO calculator. There are many ways to customize the calculator, but that's outside of the scope of this tutorial. And for our purposes, the default settings will work just fine. The final thing we need to add is some type of analysis. So we look up band structure among the blocks and add it to the workflow. In this case, it happened to be at the top of the list, but you can also use the search bar to find any block in the list. Most analysis blocks will also have some tunable parameters, and in this case, we'll be increasing the points per segment to 25 to improve the accuracy of the resulting band structure. Throughout NanoLab, you'll encounter these small help icons, which you're encouraged to click on because they open a pop-up with a small help text. And there will often also be a link that goes directly to the online manual. So this is now a minimal but complete workflow. We have a structure defining the atomic model, a calculator that determines what type of properties we can calculate for the model, and an analysis component that will extract specific data from the calculator output. The workflow is saved to disk after every change we make, and it's saved in the HDF5 format. The file can be found in both the workflow stash as well as in the data view. Now we'll send this workflow to jobs and set it up for running. We're first presented with an export dialog where we can, for instance, change the name of the results file. And if we follow through, we are first prompted to save the run script and then set up the submission settings. Here, the most important thing is to be sure we've selected the correct computer. In this example, we'll just be using the local computer, which is the one that comes pre-configured with the QuantumATK installation. There's also possibilities to add remote computing resources, and QuantumATK supports several scheduler types. Now that we're in the Jobs window, we can select our newly added job and start the calculation with the play button. Since this is a very small calculation, it only takes roughly 20 seconds on this standard work laptop. but we can jump ahead anyway. We see that the job has a check mark and the state is marked finished, so we should be able to find it now in the data view. When we find the resulting band structure results file, we can just double-click it to open the default analyzer. But I just want to show that you can also right-click and select a different option in the context menu. So here we have an interactive plot of the band structure of silicon carbide. You have some useful information extracted from the data presented numerically, such as the band gaps, and you can also edit the plot to prepare it for a presentation, manuscript, or just sharing with a colleague. When the editing is done, we can also export the plot to a suitable format. So in summary, we've gone through the basic steps to set up and perform a basic materials modeling project in QuantumATK. We created an atomic model in the builder, set up a calculation workflow, ran the calculation job, and analyzed the results. That's the end of this video, but we have many more tutorials that go more in-depth on the different parts of NanoLab, such as the data view, the builder, workflows, jobs, and working with plots. There's also tutorials on the more scientific side of things that explain, for instance, calculator choices, how to do transport calculations, how to set up molecular dynamic simulations, and much, much more. You can find all this by following the link on the screen. I hope you found this useful, and thank you for watching.